Morning, everyone. So yesterday we started into part 2 of our acid and bases chapter. We started looking at a concept called hydrolysis. Basically, when I'm given a chemical, especially a salt, which is just some general ionic compound, there's no reason for a salt to be acidic or basic. We found that very systematically, if I could break up the salt, dissociate into the positive and the negative, I would discard off any spectators, discard off any ones that definitely don't react with water. If both of them are spectators, no hydrolysis, salts will give you what you assumed, the solution should be neutral. Sometimes though, when the salt actually breaks up, sometimes the positive actually hydrolyzes. We call it cationic hydrolysis. If that happens, typically that's the conjugate acid. It's going to end up regenerating a little bit of H plus in solution, and therefore the overall solution becomes acidic, pH less than 7. If it's the anion that hydrolyzes, we end up forming a basic solution. So just to give you one quick practice question there, this will come up again in our titration problems. When we deal with a neutralization question, we're always going to have an acid react with a base. It forms a salt and water. Although at equivalence point, the acid and the base have killed each other off, we are fully expecting the pH should be exactly 7. If the salt ends up hydrolyzing, even at that equivalence point, it ends up generating a little bit of H plus, a little bit of hydroxide. More on that in a later lesson. So for just a warm-up here, I'm just going to give you a single salt here. I'm going to give you the salt here, Rb2 HPO4. And the question is just, is the solution, when I dissolve this in water, is the solution going to be acidic, basic, or neutral? Again, throughout this chapter here, I just want you to ask yourself the question, given a chemical like this, what is this? Is it an acid? Is it a base? Is it strong or weak? In this case here, I recognize, well, rubidium is a metal, the hydrogen phosphate is a polyatomic grouping here, this one is a salt. Based on your answer to that question, that actually is going to guide you for the next step. So if this is a salt, it's an alkali salt here, it's fully soluble, it's a one-way arrow. We're going to get 2 rubidium ions, and we're going to get hydrogen phosphate. Right? That was our first step. We're going to figure out if any of these are spectators. I remind you, positive spectators are any group 1 or 2 cations are spectators. So rubidium is an alkaline earth spectator, alkali spectator. So this one here is definitely, that one's not going to react with water. It's just going to swim around water, no problem. The HPO4 minus, the anionic spectators here were the top 5 conjugate bases of strong acids. Because strong acids were really good one-way arrow in coming towards becoming the base, I really have no chance of going in reverse. HPO4 minus 2 is not one of those. So I've canceled out rubidium, that one was a spectator. Your last step in the hydrolysis question is just to look for HPO4 minus 2 on the table. Again, just as a hint here, this HPO4 has an H, so probably it could be acidic, but it also has a negative charge, making it amphiprotic. So this one here could potentially be an acid or base. I need to compare the Ka and the Kb to see which one does it want to do more. So remember on your table, it actually lists both the acids and the bases. If I want to find this as an acid, it's really far down the table. HPO4 minus 2, it's in equilibrium with H plus and PO4 minus 3. The Ka constant here is 2.2 times 10 to the negative 13. Remember, these values listed as Ka tell me how good I am as an acid. Notice that this is 10 to the negative 13 here. It's not very good as an acid. I would predict that my partner is actually much better at coming backwards. HPO4 minus can also itself act as a base, so I want to look for this very same compound. A couple rows up from there, we look for it on the base side. I see HPO4 minus 2. It can actually act as a base, gain the proton, and end up forming H2PO4 minus. We always deal with just one proton transfer. I go up by an H, go up by a charge. This one here occurs at a Ka of 6.2 times 10 to the negative 8. Just be careful though, again, all they tabulate for you are Ka constants. So they tell you, for the acid, how good is my partner acid in coming forwards? What I actually want is I want to compare HPO4 minus Ka, this is the correct one. So Ka, it's 10 to the negative 13. But if HPO4 minus wanted to switch over to a base, what is the Kb constant? How much does it want to be base? Does it want to be base more than acid? Remember what we're going to do, we need the relationship. The Kb is equal to Kw divided by Ka, but be careful, it's the Ka of the conjugate. Ka of your partner. It's pretty much the Ka of the reaction that you're trying to reverse. So Kw here is 1.0 times 10 to the negative 14. The Ka of my conjugate, I'm not going to divide my own constant. I'm not going to divide how good I am at tossing a football. I'm going to divide how good is my partner in tossing the football away. So 6.2 times 10 to the negative 8. we're going to go 1e negative 14 divided by 6.2e negative 8, and this gives me here 1.6 times 10 to the negative 7. So let's take a step back here and let's say, okay, this ion here was amphiprotic. It could be acid or base. Now we just want to compare our acid and base strengths here. Since this Kb is 10 to the negative 7, that's about 1,000,000 times bigger than something that's 10 to the negative 13. So in this example here, since the Kb for your ion is actually bigger than the Ka, the base equation wins out. HPO4 minus in general is going to absorb a proton. It's going to steal a proton from water, and it's going to leave behind a lot of hydroxide. So the overall solution ends up becoming basic. All right. Our lesson is going to focus mainly on ice tables with Ka calculations. Tomorrow we'll basically repeat exactly the same lesson. It'll just take you this one added step. Because unfortunately our table doesn't list for you, oh, by the way, these are all the Kb values, we're going to actually need to do this math to actually calculate the Kb value. But aside from getting this number, the rest of the ice table stuff will be very similar to what we do today. Okay, so just be careful that the table lists for you Ka. It tells you how good your conjugate acids are in coming forwards. Okay, so in today's lesson here, I'm going to start off introducing ice tables again. It's the very same ice tables that we saw back in chapter 2, but we're just applying it to acid-base equilibrium. So this section here is 4.14. We're going to take a look at Ka calculations. All right. I'm going to start off just with a comparison here. Ka calculation could be as simple as, I want you to find the pH of 0.50 molar HCl. Okay? Again, whenever you're given a question like this, whenever you're given a compound, ask yourself, what is this guy? In the hydrolysis section, we've been saying, well, it is a salt. But in this case here, no. HCl, if I have a hydrogen, I can be willing to give off this proton here. This one here is an acid. If you decide it's an acid or base, tell me, is it strong or weak? In this case here, you check your table. Yep, HCl, chemically speaking, even though the molarity is not all that high, this one here is a strong acid. We knew from part 1 of our chapter, strong acids ionize 100%. So we're going to actually have HCl. One-way arrow gives H plus and Cl minus. That's why Cl minus was a spectator for our hydrolysis section. It really had no ability to go backwards. And being a one-way arrow, no equilibrium, we can actually predict our numbers really easily. If I start off with 0.5 molar HCl, it's a 1-to-1 ratio. This is going to break up completely. 0.5 molar H plus, 0.5 molar chloride. Even though I leave my work like that, it is understood that the HCl is completely ripped apart, completely separated, and now I'm just left over with these ions. Oh look, I already know what the H plus is. Would you be able to find pH? Well, sure. pH is negative log of H plus, so I'm going to take the negative log, in this case of 0.50. Where would I be on that ruler? Negative log of 0.5 gives you a pH of 0.30. A reminder, whenever you have pH, POH, P anything, the significant digits are only after the decimal place. That was a more standard question in part 1. In part 2, all we're going to change up here, let's see how this question is different. I want you to find the pH of 0.50 molar. Let's go back to our chiku. Okay? So most of this question is identical, right? I'm still looking for pH. That means I need to find H plus. I need to take the negative log of that. I'm still even equal molar here, 0.5 molar, 0.5 molar. But again, when you're giving a chemical, ask yourself, what is this chemical? Is it an acid, a base, or salt? Well, this one here I memorized as acetic acid. You'll find it on the left-hand side. This one here is an acid, but it's definitely not a strong acid. This one is a weak acid. What we're going to start seeing in this lesson here is that just changed everything. That just made the question a whole lot more work. And the big problem here is, yes, while you may find acetic acid on the table, being a weak acid, CH3COH, first thing is it's in equilibrium. It doesn't go in one direction. The lucky particle has managed to release off an H plus, so be it, and we're left behind with our acetate ion. I'm just going to quote the Ka value. You're going to find this on the table. I'm going to quote the Ka value. Great, this is already an acid, so this number applies directly. The Ka value is 1.8 times 10 to the negative 5. We've said this a couple times now. Well, Ka in general, notice this number here is small. So if Ka at the end of the day is products over reactants, for this fraction here to be such a tiny number, I have very few products in comparison to reactants. So this equilibrium is heavily favored towards reactant side. So while you're right, I may have 0.50 molar acetic acid, unlike the first case where it can be like, oh yeah, 1-to-1 ratio, 0.5 molar H plus, I'm actually saying this acetic acid molecule actually holds itself better that water has trouble separating off with this H+, pulling apart the H+. In fact, there's actually only tiny corner of this that actually manages to break off. In part 1 of this chapter, I just made up some numbers. Oh, maybe I get 5% dissociation, 10% dissociation. In this section here, we're actually going to calculate what it is. But what I want to just show you pictorially is it is a very tiny number in comparison to 0.5. Because this is an equilibrium reaction, we're going to set up an ice table. There's going to be some sense of time passing. The I row is going to correspond to before any dissociation. Okay, so someone has just handed you this chemical. I have 0.5 molar acetic acid. Nothing has ripped apart just yet. So we can even add in ourselves. Nothing has ionized, so no H+, no acetic acid yet. As it approaches equilibrium, albeit the Ka value is very tiny, to get towards equilibrium, some of these reactants collide with good energy, good geometry, and they're going to break off to become H+ and CH3COO. In this setup of the question here, I don't know anything about the equilibrium. So back in chapter 2, what we did is we said, okay, let's minus x on this side, because the change line, I'm going to remind you here, the change line follows the mole ratio. If my acetic acid ended up dropping by x, we know the other side, one side is minus, the other side is a plus, and they're all 1-to-1 ratios, so those are going to go up by x. I generally tell people, if you know the I and the C line, just do the math. What's 0 plus x? Well, x. 0 plus x, x. What's 0.5 minus x? Well, 0.5 minus x. Okay? I still have x as a placeholder. I still don't have the number, but at least I have a sort of a placeholder. If I find out what x is later on, I can calculate this number. Right? If you remember back in chapter 2, once you had these values here on the equilibrium row, you were ready to sub it into the Ka expression. So that's what I'm going to do here. I'm going to still write out, there's my equilibrium. I just stole it from the table. In fact, I might even want to write the complex equation. On the acid side is not too bad because I still see a column directly for H+. When we see tomorrow's lesson, when we repeat it for the Kb side, we're going to definitely want to have the complex equation. But nonetheless here, let's write out the Ka expression. The Ka expression is a product over reactants for this equilibrium. It's going to be the hydrogen concentration, multiply it by the acetate concentration, all over your acetic acid. Right? I would still write that out as the equilibrium expression, just like you did as KEQ in chapter 2, and then I'm just going to punch in my values. Great. My table has already listed for me Kas. That already tells me how good my acid is, and going forward, that's actually the number I want. So perfect. For my Chiku, 1.8 times 10 to the negative 5. I'm only going to sub in equilibrium constants, so I'm not going to sub in the 0. That was before we were at equilibrium. At equilibrium, we have an x amount on top, x amount on top. Acetic acid, the placeholder was 0.5 minus x. Mathematically, this is doable, right? It is one equation with one unknown. But if you just sort of think through the math here, the x times x will end up as a squared term. I would need to bring up this binomial later on. By distributing the Ka, and I'm going to have a term that's to the power 1 and a constant, this would end up needing a quadratic formula. Remember, I was telling you here, they work out the numbers so nicely so that in Chem 12, we don't need to use the quadratic, even though quadratic is not that bad formula. But just a simplification here, if you look back in our equilibrium chapter, how did we avoid the quadratic formula was they chose the numbers so that it was like a squared and b squared. I can just square root both sides and get rid of the square problem. This time I don't have that situation. This time I can't square root to make it look easy. This time what I'm going to do is sort of, in hindsight here, experimentally, I know that this constant here is tiny. I know that of the 0.5 molar, most of the 0.5 actually sticks around. The little corner, little fraction that actually breaks off, again, the mole ratio is fine. For every little bit that breaks off x, I'm going to get an x of H+ and also an x of acetate. But I'm going to assume that this x is so tiny that in comparison to the 0.5, pretty much 0.5, yeah, I lost that little chip here that actually went over. But 0.5 minus x here, I'm going to make an assumption. You have to write this assumption out. Just to make the math easy here, let's assume that 0.5 minus x is basically 0.5. I know it's not identical to 0.5, right? I know I'm going to lose a little bit of a tiny portion, just this corner here. But because 0.5 is expected to be so large in comparison to x, practically it's going to be 0.5. Maybe it's going to be something like 0.498. Well, if I round it back, it's just 0.5 anyways. In some sense, you are saying, yes, the x is unimportant. But I thought we were going through this math here to solve the x. X is only unimportant, negligible when comparison to 0.5. What that allows you to do mathematically then, let's just keep solving through here. 1.8 times 10 to the negative 5. The x times x becomes x squared. This bottom part just ends up becoming 0.50. And that has made the math so much easier. Because I don't have x to the power 1 term, I don't have a binomial anymore, I can bring this 0.5 up and square root, then I'm done. The caution here is you have to make sure you've written this assumption down. You have to write it out, or else it look like you were just sloppy with math. Oh yeah, just drop it, okay? No, you have to write out the assumption, okay? So let me just solve our way through the math here. The x squared 1.8e negative 5 times 0.5 gives me 9.0 times 10 to the negative 6. That's x squared, so let's take the root of that. This x is going to be 3.0 times 10 to the negative 3. Again, I was trying to tell you in the equilibrium section, yeah, it may have been a lot of math to actually solve for x. Do yourself a favor and go back and reread the question. They are interested in this question to find the pH. What did I sub in for x? Well, x was actually the placeholder. X was actually the equilibrium amount of the H+. So even though it was a lot of work to actually find this number, this is actually the concentration H+ that manages to break off. Way tiny in comparison to 0.5. This one here would be molar because it's a concentration. But even though it was more work to get to this H+, if I now know what the H+ is, I can very similarly just go, well, pH is the negative log of the H+. What would I get if I negative log this number here? The pH, negative log of this answer, gives me a pH of 2.52. Again, I still write out the whole number, but the significant digits are after the decimal place. Sig figs after the decimal. And that's just how logarithms end up working out. Okay? So, we were playing fair here. We were comparing equimolar solutions. I was dealing with a 0.5 molar solution of acetic acid versus a 0.5 molar of HCl, equal concentrations. In the strong acid case, it was just a one-way arrow. I could predict the H+ right away. In the weak acid section, I had to deal with a whole bunch of ice table, a little bit of algebra towards the end. And you notice at the end of the day, the pH for a strong acid is much lower, it's 0.3, whereas the pH on the weak acid case is actually 2.5. That really shouldn't surprise you. Well, it's a weak acid, it doesn't ionize very well. Most of it actually stays on this side. I actually break out very little bit of H+. Remember, we're on a logarithmic scale here. We can conclude that this 0.3 of a pH is about more than 2 units more to acidic, so it's even 100 times more concentrated. You can see that with the H+ concentration, the H+ in the beginning was 0.5. The H+ over here is 0.003. Okay. One other comparison I want to make here. Well, we had done this assumption just to make the math easy. Was it a good assumption? So let's just test the assumption here. You don't always need to show me this test. So testing the assumption, what if I took 0.50? I had solved through the x here based on this assumption. The x turned out to be 3.0 times 10 to the negative 3. Let's do that minus, and let's figure out, well, what number would it have gotten if I actually punched it in? 0.5 minus 3e negative 3. This one here gives you practically 0.497. Again, I want to emphasize this is not 0.5. It is true, some of this box, some of this container has actually broken off. But because the Ka value was so tiny, so little has actually broken off, you've lost 0.003, you still have 0.497. Would it be accurate for me to say, yeah, 0.497 is basically 0.5? Yes. Okay. Those of you that are really good at math here, you can try doing it without the assumption here. You can do the quadratic formula, that negative b plus or minus root, that formula there. You can solve the x, you'll practically get the same thing, and then you can just take a negative log of that and find the pH again. Okay. So the question becomes infinitely harder the second we switch from a strong thing to a weak thing. I'm just going to practice one more of these with you here. We are going to need an ice table, and we're going to see how this way of writing is a little bit different. So I want you to calculate the Ka of a 0.34 molar triprotic acid solution with a pH of 1.33. Okay. So yeah, they are still asking us about doing Ka, so it sort of fits in this section, Ka calculations. They've given us a starting concentration. Initially, before anything has broken off, you have 0.34 molar of this acid. What does this triprotic acid part tell you? Triprotic means you have 3 protons. So when I do a triprotic acid, I might write it as H3A. But nonetheless, here we always deal with just one proton transfer at a time. If I were to sort of list a heading for this H3A, the simplified equation would be H3A. It's going to lose only one proton at a time. I'm going to go down by an H, go down by a charge. I'm going to have H2A minus. That's not quite done then. This one here can still keep giving off protons, but I'm just going to study this first dissociation, this first ionization. Again, this one here is the simplified equation. Before you do your ice tables, really you should switch over to the complex equation, more important on the base side, as we'll see tomorrow. For the acid side, how do we convert over to the complex equation? Pretend to add water on both sides. What that does for my complex equation says, yep, H3A as an acid, it actually has 3 footballs to give. It doesn't just break off a football and that football just swims around in H+. The H+ is actually passed over to water. So we're going to pass it over to water, still in equilibrium. Because they're asking for a Ka, strong acids will be 100% ionized. The Ka will be very large. You see that on the table there. If they're actually asking us to calculate a numerical value, that actually tells you this guy here is weak. We can also sort of see that, well, it's a reasonable concentration. It's not overly high, and the pH here is not really deep into the strong acid region. So those would be hints that it's a weak acid. So we put an equilibrium system. We get H3O plus, and we get H2A minus at the end. Let's set up our ice table. So initially, what do we know? Initially, the concentration is 0.34. That was before any ionization has actually occurred. Before any ionization has occurred, I'd imagine all my acid was sitting here as a box. Being a weak acid, I'm going to imagine a really tiny corner actually chips off. I started off with nothing. The earlier question was, I didn't know anything about the equilibrium. I'd use minus x, plus x, and plus x, and all that. This time, they give me one added piece of information. The added piece of information is, by the end of it, the pH is actually 1.33. So I want you to picture this with me here. Start off with the container. This is labeled 0.34 molar of this H3A. Before any dissociation, I don't produce any H+. So at this moment here, the pH here should be 7. What's going to happen here is I'm going to give it a little time. I'm going to let it ionize. I know not a lot of it's going to break off, but enough it's going to break off, whether it's from the first protonation or the second one or the third one. Eventually, this pH drops from 7 down to 1.33. So there are enough H pluses in here for my pH to actually be somewhat less than 7. This part here actually would apply at equilibrium. Once everything is said and done, the pH is 1.33. This actually gives me some information for the equilibrium row. Let me just write this down again. Initial was before any dissociation. Before any breaking off at all, the pH would have been 7. By the end of it, at equilibrium, the pH is actually 1.33. If I actually know the pH at equilibrium as 1.33, would you be able to find the H plus at equilibrium? How do you get from pH to H plus? Well, I need to undo the negative log. So let's go anti-log negative pH. I can even leave it written like that. I can say, okay, then the H plus at equilibrium is just 10 to the minus 1.33. So if you're comfortable with that, you can totally do that. If you're not comfortable with having these anti-logs numbers, you can plug it in at any given point. What is the anti-log, shift log, of negative 1.33? The anti-log is just 0.046. 1.33, the significant digits are after the decimal place, so 2 sig figs. So 467, so 0.047 molar. So they actually told you, at first we were pH 7. At first we had no acid before it dissociated. But this triprotic acid here has dissociated enough to give you a concentration of 0.047. Again, you can write it as 10 to the power negative 1.33, all the power to you. If you don't like that, you can just write it out the number 0.047. Okay? So I'm given some information. At the end of the day, the pH is actually 0.047 molar H+. Well, because I know something about this equilibrium row, I can figure out the change. Starting from 0, this side had to be plus. I had to gain by 0.047. Well, these ones here are in a 1-to-1 ratio. So every time a chip actually breaks off, I'm going to gain 0.047 of the H+, 0.047 of the H2A, 0.047. This time here, the reactants are going to drop minus. It's going to drop by 0.047. Okay? Do I need to assume this time? The assume made the math easy previously because it was a quadratic. I can do this math. 0.34 minus this number here. Oh, that's just going to be 0.29. So first thing, you can make a note here. We don't need the assumption. We don't need the assumption because there's no x's involved. and there's no sort of simplification of math here, I can just subtract the number. And in fact, even if you tested it, maybe my assumption wouldn't really be valid anyways. If I tried to go 0.34, minus off the x, right? Minus off the 0.047 that I actually went over, for sure, 0.047 here is pretty tiny in comparison to 0.34, but this was actually giving me 0.29. Depending on sort of your relative context here, well, 0.29 is different from 0.34. So it may not be a really valid assumption. Usually we just bank on the fact, I'm hoping the Ka is small enough. I'm hoping so little of it actually ionizes over. I'm assuming that this assumption here will be valid. But, sort of two birds with one stone here. We didn't need to do the assumption because the math was fairly easy. I still had the equilibrium row. With the equilibrium row, I'm ready to calculate the Ka value. I just need the Ka expression then. So the Ka of my triprotic acid is the hydronium times it by the H2A minus divided by H3A. I'd still write out the equilibrium constant expression. And remember, if I have the numbers or even placeholders on the equilibrium row, these ones here are ready to be subbed into the Ka expression. So if my H plus at the end of the day was 0.047, which gave me that pH of 1.33, the H2A minus would also likewise be 0.047 divided by, I had done the subtraction. If you take this box and you figure out 0.047 actually chips off, I actually have a little bit less left over. But I know that number is 0.29. I'm going to take 0.047 times 0.047 divided by 0.29 gives me this number here. The Ka constant is 7.6 times 10 to the negative 3, give or take a little bit of rounding. Okay, this is an equilibrium constant. Again, we can conclude, well, we had expected that this was a weak acid, so this is small. Products over reactant ratio is less than 1, so therefore I can say its reactants are heavily favored. I have more reactants at equilibrium. That is still true. And in fact, this Ka is a number that actually describes my chemical. I can actually look on my table. Is there some acid there that actually has a constant somewhere close to 7.6 times 10 to the negative 3? I have one expression on the table, H3PO4 in equilibrium with H plus and H2PO4 minus. The Ka constant on the table was 7.5 times 10 to the negative 3. Sure, give or take a little bit of rounding, maybe a little bit different. We had said it was triprotic acid. I can actually then identify, oh, maybe my unknown acid is actually this phosphoric acid. So this Ka constant, it's attributed to the particular chemical. A chemical that has a Ka value of 7.5 times 10 to the negative 3 is probably phosphoric acid. One other reason why this might be slightly different, right? Obviously, I just randomly made up these numbers here. Another reason here is, remember, phosphoric acid is triprotic at the end of the day. I've only dealt with the first protonation. I've dealt with the first football that it leaves off. Well, this H2PO4 minus can also, in equilibrium, give off an H plus, form HPO4 minus 2. This one here can also give off another H plus here. There may be a few other H pluses just from the other two protonations that I'm not actually dealing with. And that's why the pH at the end, which is sort of the combination of all the H plus there is, it may actually be slightly different from just having one protonation. Okay, so definitely practice some questions in this section here. Make use of your ice tables. If it makes the math easy, do the assumption. You have to write it down. If it doesn't make the math easy, don't assume. Tomorrow we'll basically do a repeat of this lesson here, but we'll do it on the base side. The only real differences is the base side, we have to actually write out the complex equation before we write the Kb expression. And the other thing is we actually need to calculate Kb. Unfortunately, your tables only give us Ka values. I'm going to go Kw divided by my partner to get Kb. But other than that, everything is identical. Okay, so let me know if you have any questions. Thanks, guys.